Exercises of Part 4, Redox titrations. Exercise 27, we titrate V1 of Cu plus of concentration C1 by solution of cerium 4 plus of concentration C2. Write the equation of the titration reaction and calculate the equilibrium constant. We put the couples on increasing order of E, and E could not be calculated in this case since we don't have concentrations, so we put on increasing order of E0 and we apply the gamma rule. So the reaction taking place is cerium 4 plus Cu plus gives cerium 3 plus Cu2 plus. The equilibrium constant K of the reaction is given according to the relation 10 to the power n prime E0 of the cell. But since the number of electrons exchanged in the couple cerium 4 plus cerium plus 3 plus is 1 and Cu plus Cu2 plus is also 1, so n equal n prime. In this case, Kr is given by 10 to the power n0 of the cell divided by 0.0592, and n, the number of electrons exchanged in the reaction, is equal to 1. E0 of the cell is equal E0 reduction minus E0 oxidation, so equal E0 of the couple cerium 4 plus cerium 3 plus minus E0 of the couple Cu2 plus Cu plus 1.44 minus 0.153, so K of the reaction is equal 5 times 10 to the power 21. The value of K of reaction is very high, so this reaction is complete. Consider E the potential of the electrode immersed in the medium, and V2 is the volume of cerium 4 plus solution added. Calculate E for the following addition. Okay, so after addition of cerium 4 plus from the burette, it will react completely with the Cu plus present in the solution. So the reaction will reach equilibrium, and at equilibrium, E of the reaction is equal to 0. E of the system is equal E of the solution is equal E of the couples. In the titration problem, the first point or the first step is to find V equivalence in order to know if the volume added is before equivalence, at equivalence, or after equivalence. So according to the stoichiometry of the reaction, the number of moles of cerium 4 plus divided by 1 equal the number of moles of Cu plus divided by 1 reacted. So at equivalence, all Cu plus has been reacted, so the number of mole of cerium 4 plus added is equal to the number of Cu plus initial, and C2 V equivalence equals C1 V1, so the V equivalence is 40 ml. So what is the potential of the solution after addition of 20 milliliter of cerium 4 plus? V equal 12 ml is before the equivalence point. So all cerium 4 plus added to the solution will disappear completely. The initial number of mole of Cu plus in the beaker equals C1 V1 equal 4 millimole. That of cerium 4 plus added equals C2 V2 equal 1.2 millimole. So we will have a reaction between Cu plus and cerium 4 plus to give cerium 3 plus and Cu2 plus, and this reaction is complete and will reach the equilibrium. So we construct the table of conversion. At T equals 0, we have 4 millimole Cu plus, 1.2 millimole of cerium 4 plus. Cerium 4 plus will be limiting since the volume added is before equivalence. So in the final solution, we will have epsilon practically 0 and Cu plus. So we have 4 minus 1.2, 2.8, and we have 1.2 millimole of cerium C plus and 1.2 millimole of Cu2 plus. Now we have the concentrations of Cu plus and Cu2 plus, so we can calculate the potential of this couple after addition of 12 milliliter. And we know that when the reaction reaches equilibrium, E of the reaction equals 0 and E of the couples are equal. So we write E of the solution equal E of couple Cu or equal E of couple of cerium 4 plus. So is equal E0 Cu minus 0.0592 divided by 1 log Cu plus divided by Cu2 plus. So E equal, we put the number of moles of Cu plus 2.8, Cu2 plus 1.2. The number of electrons exchanged in the couple is 1, and we have the value of E0. So E of the solution is equal 0.13 volt. Suppose a student wants to work on the couple cerium 4 plus, cerium 3 plus to calculate E of the solution. In this case, we have to determine epsilon, and epsilon is calculated from the Kr of the reaction. But as we said in our explanation, before equivalence, it's easier to use the couple present in the beaker, and after equivalence, it's easier to use the couple used in the burette. For volume 20 milliliter, this is the half equivalence point. The number of mole of Cu plus is 4 millimole. The number of cerium 4 plus is 2 millimole. So we write also by the same way the table of conversion, and cerium 4 plus will disappear completely, and Cu plus we have 2 millimole and 2 millimole of cerium C plus and 2 millimole of Cu2 plus. So we apply E of the solution on the couple Cu2 plus Cu. E of the solution equal E0 equal E of the couple Cu2 plus Cu equal E0 minus 0.0592 divided by 1 log number of mole Cu plus divided by the number of mole of Cu2 plus. So E of the solution is equal E of the couple Cu equal E of the couple cerium is equal E0 of the couple Cu2 plus. Cu plus equal 0.15 volt. Is it necessary to do this calculation at half equivalence? It's not necessary to construct the table of conversion. We can say at half equivalence, half of Cu plus has been transformed to Cu2 plus, so the number of moles are equal, and directly we can apply E of the solution is equal E0 of the couple Cu2 plus Cu plus. For a volume equal 30 ml, we are before equivalence, so we use the same method. We construct the table of conversion. The number of Cu plus initial equal 4 millimole, that of cerium 4 plus added 3 millimole. So the reaction at T equal infinity cerium 4 plus is limiting, so we have epsilon, 1 millimole Cu plus, and we have 3 millimole of Cu2 plus. So now we apply Nernst equation on the couple Cu2 plus, Cu plus, E of the solution equal E of the couple Cu equal E0 minus 0.0592 divided by the number of moles of electron exchanged log NCu plus divided by NCu2 plus. We put the number of moles at T equilibrium by their values, and we obtain E of the solution equal, or E indicated equal E of Cu equal E of cerium equal 0.18 volt. For a volume equal 40 milliliters, this is the equivalence point, and at equivalence, the number of moles of cerium added is equal to the number of moles of Cu initial equal 4 millimole. So we construct the table of conversion, and in this case, we have 4 Cu2 plus, 4 cerium plus, 4 plus, 0, 0. The reaction proceeds till T equal infinity. So Cu plus and cerium 4 plus will react completely. So we have practically 0 and 0. And formation of 4 millimole of cerium 3 plus and 4 millimole of Cu2 plus. As we said, the reaction will proceed in the backward direction, but this reaction is very limited. So we have 4 minus epsilon, 4 minus epsilon, epsilon, and epsilon, and we can neglect epsilon with respect to 4. So now to calculate the potential of the solution, we can use the couple cerium 4 plus, cerium 3 plus, or Cu plus, Cu2 plus, but in the two cases, we have to calculate the value of epsilon. To avoid calculation, we pass to another method, is to write E of the solution equal ECU equal E0 minus 0.0592 log rad divided by X concentration, and the same for the couple cerium 4 plus, cerium 3 plus, E of the solution equal E0 minus 0.0592 divided by 1 log cerium 3 plus divided by cerium 4 plus. So to avoid the calculation of epsilon, in order to calculate E of the solution of the couples, we add the two expressions. So we obtain 2E equal E0 Cu plus E0 cerium minus 0.0592 log Cu plus divided Cu2 plus times cerium 3 plus divided by cerium 4 plus, and all these concentrations are at equivalence. At equivalence point, the concentration of Cu plus equal concentration of cerium 4 plus equal epsilon, and the concentration of cerium 3 plus equal the concentration of Cu2 plus equal practically 4. So E of the solution, or E indicated, is equal E0 cerium plus E0 Cu divided by 2, since log this ratio is equal to log 1, so 0, and therefore the E of the solution equal 0.79 volt. To note that we can apply the expression of E at equivalence without a proof. E of the solution at equivalence equal N1 E01 plus N2 E02 divided by N1 plus N2. What is the potential of the solution, or the potential indicated, for a volume equal 45 milliliters? This volume is after equivalence. The number of mole of Cu plus initial equal 4 millimole, and the number of moles of cerium 4 plus is equal 4.5 millimole of cerium 4 plus added. So we construct the table of conversion. We have 4.5, 0, 0. In this case, after equivalence, Cu plus is limiting, and cerium 4 plus is in excess. So practically, at T equal infinity, we have 4 minus epsilon of cerium 3 plus, 4 minus epsilon of Cu2 plus. we have 0.5 plus epsilon of cerium 4 plus and epsilon of Cu plus. We can neglect epsilon with respect to 0.5 to 4 and to 4. After equivalence, we have the concentration of cerium 4 plus and cerium 3 plus, so it's easier to work in this couple, on this couple. If we want to work on the couple Cu2 plus, Cu plus, we have to pass to calculation and to calculate the value of epsilon. To note that before equivalence, it was easier to work on the couple Cu plus, Cu2 plus. So E of the solution equal E of the couple Cu equal E of the couple cerium equal E0 minus 0.0592 divided by N1 log concentration of the rad divided by the concentration of the ox, and since V of the solution is the same, so log number of moles. Therefore, E of the solution equal 1.38 volt. Exercise 28, a solution of KMnO4 is added to ferrous solution at pH equals 0. So at equivalence point, the redox potential of the solution is 1.36 volt. Given E0 of Fe3 plus Fe2 plus, we want to calculate E0 of the couple MnO4 minus Mn2 plus. So we have a titration reaction between MnO4 minus and Fe2 plus at pH maintained equal 0. So the concentration of H plus in the solution is always 1 molar. At the equivalence point, the potential of the solution measured is equal to 1.36. How to calculate E0 of the couple MnO4 minus Mn2 plus? First of all, we have to write the global reaction MnO4 minus plus Fe2 plus give Fe3 plus plus Mn2 plus. We balance the reaction according to the Hab equation method, and we obtain stoichiometry 185514. Construct the table of conversion and apply this table of conversion at the equivalence point. Why at the equivalence point? Since in the given we have measured E equal 1.36 volt at the equivalence point. So the table of conversion can be applied at any addition of MnO4 minus to Fe2 plus, and we choose that the equivalence point. So at T equals 0, we suppose the concentration is MnO4 minus 0, concentration of H plus is maintained constant 1 molar, Fe2 plus is Fe2 plus initial 0, 0. The reaction at equivalence is complete and proceed till T equal infinity. So we have MnO4 minus 0, Fe2 plus 0, H plus remains 1 molar since the pH is maintained constant at 0. And Fe3 plus is equal to the initial concentration of Fe2 plus, and Mn2 plus is equal to the initial concentration of MnO4 minus. Then the reaction will proceed in the backward direction, which is a very limited reaction. So MnO4 minus initial minus epsilon, Fe2 plus minus 5 epsilon. We obtain 5 epsilon of Fe2 plus and epsilon of MnO4 minus. So at equivalence point, the concentration of Fe2 plus equal 5 epsilon, so equal 5 MnO4 minus at equivalence, and Fe3 plus equal 5 times concentration of Mn2 plus at equivalence. And we know when the reaction is at equilibrium, the potential of the reaction is equal 0, and the potential of the couples are equal. Since we are at equivalence, so the potentials are equal to 1.36 volt. We write the Nernst equation for each couple. E of the reaction, E of the solution is equal, or E measured is equal E of the couple Mn equal E0 minus 0.0592 divided by N log Mn2 plus divided by the ox and its components, MnO4 minus times H plus to the power 8. And E of the solution equal E measured equal E of the couple Fe, since E of the couples are equal E0 minus 0.0592 divided by 1 log Fe2 plus divided by Fec plus. So we multiply by 5, so 5E equal 5E0 minus 0.0592 log the ratio of the concentrations, and we add E and 5E, so we obtained 6E equal E0 of Mn, 5E0 Mn plus E0 of Fe minus 0.0592 log Fe2 plus divided by Fec plus Mn2 plus divided MnO4 minus H plus to the power 8. Since we apply the potential at equivalence, so these concentrations are the concentrations at the equivalence point. And at equivalence, Fe2 plus equal 5 MnO4 minus, we proved this, and Fec plus equal 5 Mn2 plus. So we put the concentration of Fe2 plus and Fec plus by their value of MnO4 minus and Mn2 plus. So 6E equal 5E0 plus E0 minus 0.0592 log 5 MnO4 minus, which is Fe2 plus, and 5 Mn2 plus, which is Fec plus. And we divide by 6, so E of the solution equal 5E0 plus E0 Fe divided by 6 minus 0.0592 divided by 6 log this ratio of concentrations. We simplify by MnO4 minus at equivalence, Mn2 plus at equivalence, 5 and 5, so we obtain log 1 over H plus to the power 8. And since H plus is equal to 1 molar, so this is log 1, so 0, and therefore E of the solution is equal 5E0 Mn plus E0 Fe divided by 5 plus 1 divided by 6. And E of the solution at equivalence equal 1.36 volt. E0 Fe is given, so we calculated E0 of the couple Mn, which is equal 1.47 volt. In part 2, if the concentration of Fe2 plus solution is decimolar, so decimolar, that means 0.1 molar, what will be the concentration of MnO4 minus and Fe2 plus in the solution at equivalence? So the concentration of Fe2 plus is 0.1 molar. At equivalence point, we proved Fe2 plus equal 5 concentration of MnO4 minus and Fec plus equal 5 concentration Mn2 plus. The reaction between Fe2 plus by MnO4 minus will transform a part of Fe2 plus to Fec plus. But in the solution, we have always Fe2 plus solution concentration plus concentration of Fec plus in the solution is equal to the concentration initial of Fe2 plus, which is equal 0.1 molar. So we have the first relation between the concentration of Fe2 plus in the solution at equivalence and that of Fec plus concentration. We apply the potential of the couple Fec plus Fe2 plus at equivalence. So E of the couple Fe3 plus Fe2 plus equal E0 minus 0.0592 divided by 1 log Fe2 plus divided by Fec plus concentration. This relation can be applied at any advancement of the reaction. One of these advancement is the equivalence point. So we apply this relation at equivalence. 1.36, the potential is equal 0.77 minus 0.0592 log Fe2 plus at equivalence divided by Fec plus at equivalence. So Fe2 plus at equivalence divided by FeC plus at equivalence is equal 1.08 times 10 to the power minus 10. This is the second relation between the concentrations of Fe2 plus and FeC plus at equivalence. So we have now two equations of two unknown. We can calculate the concentration of Fe2 plus and FeC plus in the solution at equivalence. So Fe2 plus is equal to 1.08 times 10 minus 11 molar. Then we deduce the concentration of MnO4 minus at equivalence is equal to the concentration of Fe2 plus at equivalence divided by 5. So the concentration of MnO4 minus equal 2.16 times 10 minus 11 molar. We pass to exercise 29. We add a solution of FeSO4. The volume initial is V20 ml of concentration C. A solution of K2Cr2O7 of concentration C prime equal 4 times 10 minus 2 mole per liter in acidic medium. The volume of the oxidant solution added at equivalence is V equivalence equal 12 ml. So given Fe2 plus SO4 minus ions, V equal 20 ml, we have chromate, the other couple is dichromate, the concentration 410 minus 2, and the V equivalence is equal to 12 ml. 29.1, the global reaction is, so we write the reaction between Cr2O7 2 minus and Fe2 plus to produce FeC plus and chromium 3 plus. And we balance this reaction according to the method of the Have equations. We obtain the stoichiometry 114.6.627. So the correct answer is B. Exercise 29.2, the equilibrium constant of this reaction is, the equilibrium constant is given according to the relation K equal 10 to the power n prime E0 cell divided by 0.0592. So n equal 1 and n prime equals 6. So n equals 6. E0 of the cell 1.36 minus 0.77 divided by 0.0592. So K equal 5.71 times 10 to the power 56. So the correct answer is A. The value of K, as you observed, is very high, so this reaction is complete. The initial concentration of Fe2 plus ion is, we calculate this concentration at equivalence, since according to the stoichiometric ratio, the number of mole of dichromate divided by 1 reacted is equal to the number of mole of Fe2 plus reacted divided by 6. At equivalence point, all Fe2 plus has been reacted, so the number of dichromate added is equal to the number of Fe2 plus initial divided by 6. 6 times the concentration of dichromate is C prime V equivalence equals CV, and we calculated the concentration of Fe2 plus equal 0.14 molar. So the correct answer is C. Exercise 29.4, the potential electrode is measured with respect to hydrogen electrode. Give the expression of E as a function of V prime, and V prime is the volume of dichromate added for a V prime between 0 and 12 milliliter. So between 0 and 12 milliliter, the volume of the dichromate added is before equivalence. That means the ion present in the beaker is in excess. And after each addition, E of the reaction is equal to 0, and E of the solution is equal to E of the coupled dichromate chromium C plus and equal E of the couple FeC plus Fe2 plus. Since the volume added is before equivalence, so it's easier to use the couple present in beaker. So we will work on the couple FeC plus Fe2 plus. FeC plus 1 electron give Fe2 plus, so E equal E of the solution equal E of the couple FeC plus Fe2 plus equal E0 minus 0.0592 divided by 1 log concentration of Fe2 plus divided by FeC plus, and since the volume is the same, so it's equal to log number of moles ratio. We construct the table of conversion as in the previous exercises. So at T equals 0, we have N prime dichromate, we have N of Fe2 plus, 1 molar H plus, 0, 0. The quantity reacted, dichromate is limiting since we are before equivalence. So minus N prime. If we lose N prime of dichromate, we have to lose 6 N prime with Fe2 plus. So we have minus 6 N prime reacted. The concentration is always intact. 1 molar, since the solution is buffered. We have 2 N prime formed chromium 3 plus and 6 N prime of FeC plus. So at equilibrium, at T equal infinity, we have a practically 0 of dichromate, N minus 6 N prime, 1 molar, 2 N prime, and 6 N prime. Then the reaction will shift in the backward direction, and the reaction is very limited. So we have 6 N prime minus 6 epsilon, 2 N prime minus 2 epsilon, and we neglect epsilon. And we have N minus 6 N prime plus 6 epsilon, we neglect also epsilon. And here we have epsilon of dichromate. So the number of mole of Fe2 plus equal at equilibrium is equal N minus 6 N prime equal C times V minus 6 C prime V prime. To note that C, V, C prime, and V prime are given. And the number of mole of FeC plus equal 6 N prime equal 6 C prime V prime. At equivalence point, we construct also the table of conversion, but in this case, N prime and N are equal. So we have N, and we have here epsilon and 6 epsilon, 2N minus 2 epsilon, and 6N minus 6 epsilon. The number of mole of Fe2 plus at equivalence is equal to 6 times epsilon. So the number of mole of Fe2 plus at equivalence equals 6 times the number of mole of dichromate at equivalence. And at equivalence, the number of mole of Fe2 plus, which has been reacted completely, so this is the number of mole of Fe2 plus initial, equals 6 the number of mole of dichromate at equivalence. So C times V equal 6 C prime V equivalence. Why we use the table of conversion at equivalence? Since we want only to find a relation between C, V, C prime, and V equivalence to be used later. So now we return to the volume which is before equivalence. The number of mole of Fe2 plus equal N minus 6 N prime, CV minus 6 C prime V prime. And we replace CV by its value of C prime V equivalence. So 6 C prime V equivalence minus 6 C prime V prime. So equals 6 C prime V equivalence minus V prime. And the number of mole of FeC plus is equal practically 6 N prime. In the previous table of conversion is equal 6 N prime. So equal 6 C prime V prime. We apply Nernst equation on the system FeC plus Fe2 plus, and here we observe the appearance of C prime, V equivalence, V prime, C prime, and V prime. We simplify by C prime, so E of the system equal 0.77 plus 0.0592 log V prime divided by V equivalence minus V prime. So the correct answer is D. Exercise 29.5, calculate the potential E for a volume between 12 and 25 milliliters. This volume is after equivalence, so the dichromate is in excess, and it's easier to calculate E of the system by using the couple dichromate chromium 3+. So we write E equal E0 of the couple minus 0.0592 divided by 6 log chromium 2 divided by H plus to the power 14 Cr2O7 to minus concentration. We construct the table of conversion. We suppose the dichromate is the number of moles is N prime, and Fe2 plus the number of moles is N, and H plus is buffered at 1, so it's intact, and chromium 0, FeC plus 0. The quantity reacted, we calculated the quantity reacted. Since dichromate is excess, so Fe2 plus is limiting and it will react completely. For N reacted of Fe2 plus, we have N over 6 reacted of dichromate. So at equilibrium, we have N prime minus N over 6, 0, 2N divided by 6, and N. Then the reaction shift in backward direction. So we have N minus 6 epsilon, 2N divided by 6 minus 2 epsilon, 6 epsilon, and N prime minus N over 6 plus epsilon. We can neglect epsilon with respect to N, with respect to N over 6, and with respect to N prime minus N over 6. So we have appearance of epsilon only for Fe2 plus. At equivalence point, we found the relation 6C prime V equivalence equals CV in the previous part. So the number of dichromate is equal, in excess, is equal N prime minus N over 6, N prime equals C prime V prime minus CV divided by 6. We put CV by its value, so it's C prime V prime minus 6 C prime V equivalence divided by 6. So the number of dichromate in excess is equal C prime times V prime minus V equivalence. The number of mole of chromium equal to N divided by 6 equal CV over 2CV over 6 equal CV over 3, 6C prime V equivalence divided by 3, so equal to C prime V equivalence. Now we apply E of the system equal E0 of the couple dichromate chromium 3 plus, we have to correct, equal E0 minus 0.0596 log ratio of the concentrations, and we find the concentrations since we determine the number of moles, and to note that V total equal V plus V prime. So H plus equal 1 molar, and the relation is E of the system equal E0 minus 0.0592 divided by 6 log chromium 3 plus square divided by dichromate, and we put this concentration by their values found here. So E equal E0 minus 0.0592 divided by 6, 2C prime V equivalence divided by V plus V prime square divided by C prime V prime minus V equivalence divided by V plus V prime. We simplify by V plus V prime, and we obtain this relation. So log 4 C prime square V equivalence square divided by C prime. We simplify by C prime, and then we obtain the relation E of the system equal E0 minus 0.0592 divided by 6 log 4 C prime V equivalence square divided by V plus V prime times V prime minus V equivalence. So the correct answer is B. Exercise 29.6, calculate the potential E for a volume equal 12 ml. So at equivalence point, we have always 6 C prime V equivalence equals CV. The potential of the solution or of the system at equivalence equal EFE equal E0 FE minus 0.0592 divided by 1 log FE2 plus divided by FEC plus, and E is also equal to E of chromium couple equal E0 minus 0.0592 divided by 6 log ratio of the concentrations. So we multiply E of the chromium by 6 and we add it to E of Fe. So we obtain 6E plus E. So in total 7E equal 6E0 chromium plus E0 Fe minus 0.0592 log ratio of concentrations. So at equivalence, we have Fe2 plus equals 6 dichromate and Fe2 plus equals 3 chromium. We put this concentrations according to dichromate and chromium, and we found this relation. Since H plus is equal to 1 molar, so E at equivalence, this volume, equals 6 E0 chromium plus 1 E0 Fe divided by 6 plus 1 equals 7, minus 0.0592 divided by N divided by 7 log 2 chromium concentration. So what is the chromium concentration at equivalence? The number of mole of chromium is equal to number of mole of dichromate. So the number of mole of chromium C plus equal to C prime V equivalence divided by V total. So 2 C prime V equivalence divided by V plus V prime. The V is 20 ml plus V added 12. So chromium equal 2 times 12 divided by 4 10 minus 2 divided by V 20, and the volume added at equivalence is 12, so equal 0.03. Then E equivalence, the potential of the solution at equivalence is equal to 1.26 volt.